我开始了。这个发展其实历史啊，怎么讲，不到200年吧。它如果talk about branching process, there's 3 names attached to this. ，Epidemiology， 这大概是还有是。这大概是1840几年，45年左右。这个是大概10几年以后，1870年左右。但是事实上，现在我们 talk about branching process， 这个很有意思的是，这个人是第一个，相当于是 formulate branching process， 然后 the mathematical rate， 但是 nobody actually pay attention， 然后 simply forget in history，even if he did it early。然后 later 是 Kaohsiung 和 Watson， 他们呢就是他俩的 name 事实上 attached to process。branching process， 很多时候我们也许应该讲，Benami Kaohsiung Watson branching process， 但事实上一般来说只有这2个人的名字，你看 paper 和文章的时候会是他们。而问题是什么呢？这2个人 make the process become well recognized， 但是他们 whatever the mathematics they carry out actually was not fully right。All right， 那为什么最开始人们感兴趣 branching process？ 我们来画个图吧。然后，就是你可以想，这个是 zeroth generation， 然后这个是 the first generation， 这是 second generation。那最开始从比如说我们就是最开始的时候，我们假设只有1个人，然后是每一个 generation 它都 independently generate their offspring。第一个是 generation 的 process 是 independent， 比如说下一次它生成2个 offspring，like brilliant children， 那这2个 children 再 produce 他们的 offspring， 然后他假定这个都是 independent， 然后还 follow the same law。 We start with one say individual， 然后呢我们假定 each individual它会 generate a random number offspring。然后 we also assume each offspring 或者 each child each child has a number of 也是 random number。就说这个问题为什么刚开始从引入的时候没有人注意，后来是说到这个时间大概开始人们 pay attention， 就是说当时在欧洲有很多那个 family 它 attached to a big name， 然后大家感兴趣的问题是说 这个 family 它会不会 eventually survive， 还是说它这个 family， 你看，你看中国历史上有很多比较特殊的那个 surname last name， 比如说司马现在可能还会见到，对吧？然后还有什么？我想想啊，那个独孤，就是有一些，它事实上在远古的时候，它都有很大的家族。那现在的问题说，比如说现在可能大家就是认识的人里、知道的人里，可能比如说姓司马的可能还有，但是独孤的是不是可能就变得很少，或者比较少，几乎没有碰到？那当时的欧洲的人，他感兴趣的问题说，这是几个，比如说皇室爵位的，他们这个大家族 attached to 这个 name， 它能不能 eventually survive？ 那如果能 survive， 或者是说 extinct， 那它 what's the survival probability？ 所以他们就用这样的一个 process 去研究，当时的相当于是 family survival 问题。那它基本的假设是什么呢？这是它的 basic assumption。有3个，第一个是什么？第一个是说，there's 3 basic assumptions attached to branching process. The first one, each individual in the generation any generation gave birth to so many offspring. So here, Yn is a random variable with probability density function, or the offspring probability density function. So, 这什么意思呢？ So when k equals 0, say give birth no offspring, no children. When k equals 1, what's the probability you give birth to 1 children or 1 child, and etc. The second one is independency. What this is saying is each individual gave birth independently. You know, that's a super strong assumption. So doesn't matter which generation, you always give birth to give birth to children, but independent of from any other cases, from all other individuals. Yeah, in another word, say the production of offspring is independent among each other. This is a super strong assumption. And the last one is identical. Identical is saying what? Identical is saying here is the individual in the nth generation, this one. And they follow the same law. This is in distribution sense. They're probably not identical, but in distribution, they have the same PDF, CDF, and movement generation. For all of them. So what this is telling us, let's say X0 start with one parent. And X1 is equal to what? Because you only have one parent. So it's going to produce so many offspring, so many children. You with me? Then X2 will be what? Now how many in terms of the first generation? So you have X1 offspring. Now those X1, each of them will produce Y offspring. So you're going to see Y1, that's whatever the first individual comes from the first generation, and second individual. And then goes all the way to what? X1. Suppose like the cartoon we just saw, and in this case, X1 is 2 in this realization. Then X2 would be Y1 plus Y2. The first generation produces 3 children or 3 offspring, and this will be X1 equal to 3. So X2 will be Y1, Y2, and Y3. So, and this index actually is also a random variable. So Xn is going to be what? Y1, Y2 plus Yxn minus 1. So that's what the basically set up. Now for this one, in the general result, and the key things I want to talk about the generating function. Remember, and we discussed before, so if we know the generating function, we're going to be able to supposed to recover everything about this process. So let's see this. If we define f of t to be the probability generating function, this is the probability generating function of a random variable, generating function, let's say y. Remember, by definition, this is what? This is expected value of e to the power y. How we're going to calculate this? We replace y by all the possible values. It's going to take all the possible k's. So this is t to the k. Then times the probability. This is the probability y equal to beta. So this is the average. And this is how we define the probability generating function. We saw this. Now, I'm going to clean this piece. Sorry. Now, remember we assumed X0 equal to 1. Now we let Hn of t be the probability generating function of Xn. So now we know when n equals to 0, H0 of t is what? H0 of t, let's see this, is expected value e to the power x0. X0 is 1, right? So this is expected value of t to the power 1, but this is nothing random. So this is exactly. So this is the beginning moment generating function. The n equal to 1, the first generation. This is expected value t to the x1. Or what's x1? X1 is what? Because you only produce 1, not produce 1. That's how we start. So we only have 1 parent. So this case, that's exactly f. Look at the definition, right? That's the probability generating function of 1. The n equal to 2, we use total law of probability. Just one step derivation. So we will see e to the x2. This is going to be what? It's f of t. In other words, is the compound or composition of f. So that's why and probability generating function is convenient. So we have the following result. And this is one of the key for branching process. Suppose I start with 1 parent and yn all the way in is a family of IID random variable. We still remember what's IID? Identically independent distributed random variables with probability generating functions. In other words, doesn't matter which one you are, you follow this distribution, this identical distribution, meaning they follow the same way to produce the next generation, just like cell division, like proliferation. They pretty much follow the same law to produce the next generation. So what's the key result? Then the PDF, what we saw of the nth generation, is given by this. So how we did it? If we get the first generation, we got the PDF. Now, if we do this, apply the same PDF again, it's like what? F apply on the PDF of the before generation. So we get this, and so this is the key. All right, so let me see if I can find a simple example for you guys, for everyone, so we can at least get a little bit idea about this. Suppose let's consider branching process. Branching process. Okay, with again x0 equal to 1 is just a simple application. If we understand, if we start with 1, what happened, we know what happened to if you have 2 parents, 3 parents, etc. So then, what is the offspring distribution? This P0 is probability y equal to 0. Yes, P1 is probability to produce 1. So this is 1/4. This is 3/4. What this means? This is saying each generation, they either produce no children or no child, or one child, no more. They cannot produce 2 more. because the probability those two add up is already 1. All right, here's the setup. So now what's the question? What's the probability that the population survive? So now the key is we know we have this result. So if we know the probability generating function or offspring production function, we know we're going to know f of t, right? So now, as assumption, what do we know? The PDF of the offspring. Why? Basically, it's what? It's how you start with one guy, one parent, how that's going to produce the next generation, the law. So what's the PDF? Let's see this. PDF by definition is what? Summation pk, oh, I erase that, t to the power k. Well, k is greater or equal to 0. So it's like you have a series, and the coefficient attached to a series is the corresponding probability. And now in this case, each generation, each individual only produce at most one child. So we only have what? For all this index, we only have P0. Actually say is because this implies k is greater or equal to 2 is all 0, right? So we only have how many terms left? We only have the very beginning first 2 terms left, which is what? P0 plus P1t and P2t squared and P3 e to the power q, etc. They're all gone because there's no probability you're going to produce more than one offspring. You with me? So what's P0? We know it, right? 1/4. This is 3/4. So this is what we got. And now, by the result, we just see. So now the PDF of not x2 is what? It's going to be h2. It's going to be the composition of this one. So what we did P0 plus P1, you're going to replace T by F of T. Like a composition, right? So if you plug in everything we got, what do we see? We saw this. Then in general, by induction step, we see this. This is the nth composition, which gives us this power. All right. So now I got a question. What's this quantity telling us? And what's this quantity telling us? This is what happened. The PDF for the is the PDF probability general function of nth generation, right? Follow this law. But why this matters? What this telling us? This is the probability the nth generation produce no child, no offspring. This is the probability the nth generation produce one child. There's no likelihood, there's no chance the nth generation, any individual from the nth generation going to produce more than one offspring. So anything beyond that, that's zero. If we know this, so what's the ultimate extinction probability? Is what? Is the limit. This is what? P0, right? This is P1. So is nth generation, then goes to infinity. This is P0 at the nth generation. This is the probability nth generation produce one, right? There are no more. So this is what? And what's this limit as n goes to infinity? So what's this is saying? If the big family attached to that name, and here, if this is a simple law, how they produce child, the next generation, right? And now eventually you see this big family will be gone. That's all this is saying. So far, so good. 这个就是说，如果你知道了它的 probability generating function, 你知道 the law that how they're going to produce each generation. Of course, you can do a lot of things. And this is the things, this is basically the question we asked in the very beginning. Now let's see how that's going to be related to what? To epidemiology, infectious disease. Are we together? So the key is this, right? Is this one. If you know the PDF, the first generation, you know the PDF, second generation, third generation, etc. So it's basically the composition of the PDF. That's why we use PDF. If you use any other quantity, like to describe the process, we're not going to have anything as convenient as this. That's the first thing. Okay, all right. So now I hope we got at least the big picture about branching process. Benami, Gaussian, Watson branching process. But usually people simply say Gaussian-Watson branching process. Now, epidemic. So, and the branching process, the Gaussian-Watson branching process, or the BGW branching process can be applied to epidemiology. So we will use a simple example to illustrate and to talk about this idea. Let's say IoT to be the number of new infections. Or new cases. A time. And we made the following assumption. We assume first one, we only consider the integer time. So from t to t plus 1. The new infected individual, the new cases. Are generated by what? By contact. between the new cases at time t. And the current susceptible population. That's how the new cases, like the offspring, is going to produce each step. Second thing. And of course, we are assuming each infected individual independency is independent of all other infected. So whatever happened to other infected cases and has no influence on other new cases. And the last one is they follow the same law. But here in particular, we're assuming any infected individual is going to produce on average R0 new cases. Is the setup okay? First one is saying how we're going to produce new cases. And second thing is talk about independency. Of course, it's a huge assumption. And the last one, they follow the same law. Not only that, they're going to produce on average R0 number of new cases. All right, so let's say PK be the probability sequence. Probability distribution of the new infection produced by one infected. So in other words, T0 is saying one infected individual, whatever the infected you concern, your reference, what's the likelihood produce no new case? And P1 will be the probability to produce one new case. And K equal to 2 will be probability to produce 2 new cases, etc. Here is just set up. So then we know the probability generating function of new infection or new cases is what? Is going to be summation, is a series. What's the coefficient? Is the distribution, PK. Then from assumption, let's see, what's the derivative? The derivative, of course, this is infinite series. There is a problem between infinite summation and derivation. How come they can be interchanged? So that's related to uniform convergence. But if that's true, how are you going to differentiate? You get what's the derivative? This is derivative with respect to t. 这导数是什么？是关于它的 PK 是 constant 是吧？ What's the derivative? What's the derivative t to the power k? We all know this, right? So this k will be bigger or equal to 1. The first constant will be gone, right? Now, of course, what's this telling us? What's one? When you evaluate this as one, what do you got? You got summation KPK. What's that? That's exactly the average new infection produced by one individual. This is the average. This is the number of production times the probability how it's produced. That's the average, which equal to what by assumption? Which is equal to each individual, no matter what's their generation, produce actually what? Give birth to how many new cases? How many new cases? Or not? Then what this means? That means the average, this is how things produce. The average of new production is what? Is R0. All this is saying, you think about very beginning of any disease or any production of the disease, you start with very few, as without loss of generality, let's say 1, and how things is going to be developed over time. What this is saying, start from the very beginning, each individual on average produce what? R not number of next generation or children or offspring. If you have that picture in your mind, you can think about if R0 on average less than 1, what do you expect? And yeah, exactly. If R0 on average, right, less than 1, that's saying this family, whatever the surname, no matter how big, is going to eventually stay. And the smaller the R0, the faster of the extinction. The family name will be gone, right? Or like the extinction will be gone. This R0, basically why I use R0, that's basically the basic reproduction number. And the other thing, if you flip the coin to see the other side, if R0 is big, say bigger than 1, say 2, 3, then you can think about, start from first generation, suppose R0 is 2, on average, you're going to produce 2 offspring. So how things is going to branch, right? Branching. It's like branching. If R0 is bigger than 1, what do you expect? You're not going to expect the process will go extinct, right? Do you have that picture in your mind?
So
Think about the very beginning of the cartoon we just draw and saying, start with 1 infected. If on average I produce, let's say R0 equal to 2, on average I produce 2 children, then you keep this pattern. I'm not saying exactly 2 because that's the average. Sometimes could be small, sometimes could be big. Then things you're going to expect what? Ultimately, and the infection is not going to extinct. Yes, back to you.
so the time t and t plus 1 is just for unit time?
Like
It's all the
integer,
generation.
integer. Now it's all integer.
The integers.
Yeah.
But like days or
Yeah. Like days, hours, weeks, it depends on how you measure the time. Yeah.
R naught is for the generation to generation,
Yeah,
not for unit time.
yeah.
And how these two match?
This two match is saying, and the production of the disease is not like what you think about for what? This is a production, and for the disease case, it's not for like family case. And say on average, you take at least 20 years to produce, 20, 30 years, I don't know, like 15 to 30 years to produce the next generation. That's the corresponding time. But for the disease case, now we're assuming start from the beginning and every time unit, whatever the production time unit that is, and that's how they're going to branch.
So R naught is not the average production per unit time. It is the average production per unit generation. Generation may be the more than 1 unit time.
Yes.
Like in COVID-19.
Yeah.
It's
Yeah.
a
This is a right.
10.
Right.
So R naught means within the 10 days, it produced the 2 point something like that.
Right, so now that's why we didn't specify what's this.
Yeah.
It's,
If you are taking per unit time, that is per day. So per day, exactly R not produced.
so in that case, basically, if you want to do per day, suppose you know the generation time, capital T, right? And here's a little t. Now you can do what? You can do this. Divide the whole thing by this. It just average production per
Definitely.
unit time. You can do that.
Yeah.
But now what I'm saying this is over generation, how things is produced. Ideal or the logic wise, they're the similar, just the constant you have to resize. Okay? And so now because branching process talk about what? You produce offspring. So what that time means? The time from one generation to the other generation. That's exactly the time in between. That's exactly the time in between. But suppose you want to look into things per day, per week, or per month. And of course, you can always resize this because that means the average production, whatever your unit is, right? Yeah, you can do that. That's a great question. But now back to this. What do we want to know? We want to know what's the probability the disease will be what? Will be extinct, right? What's the probability disease will be extinct? We like that. We don't like the persistence of disease. So the key question is, or the important question is what? So what's the ultimate extinction probability of whatever the disease you care about, and which can be summarized in the following result. That's called theorem 2. Suppose the PDF, the probability generation function, f of t satisfy the following condition. Let's see what each of those means in a second. And then furthermore, we're assuming initial conditions. Let's see this. This is probably the simplest. This is saying initially how many infected individuals we have. I naught. Doesn't have to be 1. Could be any positive integer with probability 1. Let's see what this means. What's F0? F is this. What's F0? F is what's F0? P naught. What's F prime at 0? P1, right? You can think about this, what? You differentiate this and then evaluate 0, and that's the only thing left. Or you think about Taylor theory. But now the point is, what's the first assumption? Assumption is saying there is a positive probability the disease will. This is how each individual will produce new infection. This is saying there's still a chance, a positive chance, it's going to produce no what? No new cases. You can produce 0, 1, 2, etc. But now this is saying there's a chance you produce nothing. And second, what's this? What's P1? P1 is what's the chance you produce exactly 1 new case. And the whole thing, this is P0 plus P1 less than 1 is saying what? There is a chance you can produce more than 1 new cases. Are you with me? F of 0 is less than 1. Oh, sorry, bigger than 0 is saying there is a chance you produce nothing. And the second assumption, F0 plus F prime 0 is less than 1 is saying what? P0 plus P1 less than 1. That means you must have some PK. K is bigger than 1. Because what? Because the whole summation is 1, right? If P0 plus P1 is less than 1, you must have something else left. But when there is something else left, let's say you can find a K. K must be bigger than 1. And PK such that PK is positive. So what that means? That means there is a likelihood you're going to produce more than K new cases. What's the chance? PK. But in the branching process, if you look at the classical book and terminology, that means if F0 plus F prime 0 is equal to 1, that's an irreducible case, meaning a trivial case. So we're not going to look into that. Anyway, you got the meaning of this. There is a positive probability, and each individual, infected individual, can produce more than 1 new cases. So far, so good? And the last one is the initial condition. That's all. Are you with me? So now, let's say if R0 is less or equal to 1. Doesn't matter is SIS, SLR. Remember, when R0 less or equal to 1, what happened? Disease will die, right? Will die. Then let's see, what's the branching process result? The limit probability, IoT, is the number of infected at T's generation equal to 0 as T goes to infinity, it's 1. Disease ultimate extinction probability is 1. But if R0 is bigger than 1, then this quantity is what? Equal to Q power I0 plus Q, where Q is the unique fixed point of F of T equal to T in what? 0. Let's see if you notice for F of T, when you plug in T equal to 1, what do we got? We got summation P to the power K times 1. What's this? This is summing over all the possible probability, which is 1. So F1 is 1. 1 is automatically a fixed point of the PGF no matter what. No matter what the situation is. But now we're talking about within. I should make this one even stronger, not here. Inside the unit interval, because it's a probability, strictly between 0 and 1, you can find the unique fixed point of Ft, meaning Ft equal to T. So in other words, if we know Q, we know the initial situation, we will know what's the ultimate extinction probability. Let's see an example before we verify this. So let's see an example first. Suppose we talked about Poisson process before. Suppose IFT, the number of new cases as T's generation, follows a Poisson distribution and with lambda equal to R2. Okay? a Poisson distribution. Fixed t is a Poisson random variable. And now the PDF, this case, is p to the k times t to the power k. But for Poisson cases, what's the probability? It is e to the negative lambda, lambda to power k, k factorial. So if you simplify this, this is exactly e to the negative r0, 1 minus t. So we know the PDF. Now, this is assuming the new production follow Poisson process. And of course, you know the PDF because you know the probability distribution, you know the PDF. So then by the theorem, the second theorem, what do we know? So then we know Q is going to be the fixed point of this one. No, not no T, here's Q. F of Q. This is tricky, right? The fixed point of the PDF. That's how we determine the ultimate extinction probability. Then we can calculate, suppose, say, let's do a table. Suppose here's R0 value, and here is, and suppose I start with I0 equal to 1 infected individual, follow branching process. Eventually, what's the ultimate probability extinction? But what we really care about is the probability of epidemic. If you are not extinct, then you get the what? Epidemic probability. So suppose R0 equal to 1.5, you solve the fixed point for this, and you see the epidemic probability in this case is 58.3%. In other words, 1 minus this will be the ultimate extinction probability. If you are not extinct, you will see the likelihood for epidemic. What's the epidemic probability? 1 minus Q. All right, so suppose R0 equal to, let me do one more scenario, adding an I0. I not. So this will be I0. This is I0 equal to 1. What if I start with 2 infected individuals? Then this probability, this is 1 minus Q, this is 1 minus Q squared. Okay? The same Q we got. And then what's this? This case is, let's see if that makes sense. This is saying, suppose I know the extinction probability, start with 1 individual. But if I have 2, then this is saying is Q times Q. The probability is going up or down. When you have more people initially getting infected, your extinction probability intuitively will go up or down.
That's an interesting thing, because in generally deterministic model, it is not matter that how we start the epidemics in the beginning.
Yeah, that's a fundamental difference
Yeah.
between determinate sense because they.
But here, if you start from the higher number,
Uh-huh.
then there is high chance of the epidemic remains in the community, like that.
Right. So if you start with I0, meaning the initial number of individual is higher, then Q is the same thing, right?
Yeah.
And Q, but unfortunately, Q is a number between 0 and 1, the fraction, right? So when I0 is big, the ultimate extinction probability will be less. In other words, the likelihood of epidemic will be higher. All this is saying when I0 is higher, because the first case, why we didn't calculate the first case, we know the ultimate extinction probability is 1. So the only thing might be interesting will be what happens when R0 is bigger than 1. Okay, let's see one more example. Suppose R0 equal to 2, 2, and I0 equal to 2. So this 1 minus q squared is equal to almost 96% of the chance you're going to see what? Epidemic. Extinction probability is extremely low. What's the difference? I slightly increase R0, and initial number of individuals still 2. The chance is pretty low. But then that actually we see the fundamental difference between, before we see so many cases, doesn't matter SIS, SIR, and some other things. What do we saw? The fundamental idea for those basic or classical model is when R0 is bigger than 1. You expect? Yeah, disease persists, and you probably eventually end up some endemic state. But that means the ultimate extinction probability will be 0, right? However, here we say there is a chance and the situation, or maybe you end up the disease die off, but just how likely. The larger of that quantity q to the power I0, the higher chance. You can think about even each generation and start with very beginning first infected individual. Over one generation, one infectious period, okay? And now even R0 is 2, anything can happen. This is saying the chance is just low. It's less than 5%. 1 minus that, less than 5%. But still, there's a chance the disease or the infection might become extinct or might die off.
I think that's the reality.
Yeah, that's the key point. But now the question is, we haven't proved or anything showed us. Now the question I want to emphasize is, and you may wondering under what situation maybe branching process, because before we talk about Markov process, right? Branching process might be a good approximation. When we start with the very beginning. So very beginning means I0 is pretty much close to 0, say 1 or 2, 3, very few. And you talk about initiation of the disease. So this might be a good model. And it turns out we're not be able to do anything here, but one comment we can do is, if you have, for instance, Markov chain, that's a nonlinear process. Nonlinear because in between some terms, just like even mass action, remember? And what's the force of the infection or the reduction of production new infection rate is the beta SI. Because you involve 2 components, 2 variables, that's nonlinear. So the doesn't matter DTMC or CTMC you talk about, that's a nonlinear stochastic process. But when you do this, it's like what? The analog, I have a nonlinear ODE. Now I linearize the situation at what? Disease-free, which give us a linear system. So this one, the branching process, is like a linearization nonlinear process near disease-free steady state. This is the second key. All right, I'll sketch how we're going to see this result now. You guys get a little bit of idea? There's going to be a fundamental difference. The difference coming from here. But when the branching process might be a good approach, an even better approach. When the disease simply just started, the ODE model, let's talk about the average, right? The ODE model, that's the average behavior. And probably it's not going to be very appropriate because you talk about how things is start in the very beginning. Everything is integer and random process. And also second thing is, no matter what's the chance, whenever R0 is bigger than 1, you're going to see a positive probability that ultimate extinction will take place. Even though sometimes this quantity or this probability might be small. All right, so now let's see how we're going to check certain. So the key is what? Let's do this. We talked about the ultimate extinction probability. I'll start with one infected. The probability IT equals to 0. The T's generation, given initially I only have one infected individual. This is, you start with one guy. After how many generation, T generation, you're done. What's the likelihood, QT? And the problem we ask is what's the limit QT when T goes to infinity? That's the question we ask over there. You guys with me? Okay, this is a given. This is given. Now simply I start with little I0 is 1. All right, so now if we use, this is total probability law, total law of probability. Plus independency of the branching process. So that's a property number 2, property of branching process. So what do we know? We know this. The next generation is going to have the following recursive relationship. The same way as how we derive the relationship between, similar way as how we derive the relationship between the probability is a composition. You keep applying F. What's this? Q0 is whatever you know in the very beginning. And oh, what's Q0? Can you guys see? Initially, you have one infected individual. You ask, what's the probability initially this will be 0? Can anyone tell us? This is saying I start with one guy, but this asks, what's the probability at the starting point I go extinct? Is that possible? Not possible, so what's the probability? It's an impossible event, so the probability is going to be 0. So that's how we start. And then Q1 will be F of Q0, will be F of 0. Then Q2 will be F of Q1. So we got this. It's a recursive relationship. But because what? So first you can show this is a monotonic increasing sequence in terms of T, and it's bounded about by 1. If you have monotonic sequence bounded about by something, so what are you going to know? You're going to know this monotonic sequence must have a limit, right? Because you have upper bound. So second thing, F is what? Is a strictly convex function. How you see this? Just differentiate. First derivative telling you is monotonic, second derivative telling you the convexity. Because of this, so this telling us this one can only has at most 2 fixed points. But one fixed point you already know. What's the trivial fixed point? Will you plug in t equal to 1, remember? This must be 1. 1 is a fixed point. So now the question, do we have the other fixed point? So now let's see this. If R0 less or equal to 1, one picture I think will be clear. Let's see this. So now this is diagonal. This is 1, 1. When t equal to 1, f1 is equal to 1. But what do we know? We know f prime, remember R0 equal to what? The derivative generating function evaluate at 1, right? Sorry, I already erased that. That was in the last note. Do we remember those? Because f prime 1 is a mean. It's summation ktk. This is the value you took times the probability is going to happen. The sum is mean, right? But we know on average, each individual produce R0 number of new cases per generation, right? You guys with me? So now here is the key. If R0 less than 1, R0 is the slope of f at 1. Less than 1, how does it look like? It looks like this, right? We have another color. This is f2. We can rigorous prove this. The point is at 1 is a fixed point, so you're going through 1, 1. Second, the slope f prime at 1 is what? Is less or equal to 1. So you compare to diagonal exactly is 1. You are above the no fixed point. If no fixed point, the ultimate extinction probability, because this one has at most 2 fixed points. If inside no fixed point, so the only fixed point left is 1. So the ultimate extinction probability is 1. Second case. Sorry, I don't want to erase the theorem. I'm going to erase this piece. Is that okay? Or I'm going to erase this piece. Let's see the second scenario. Second scenario. Case 2. R0 is bigger than 1. Again, what's R0? R0 is the slope of f at 1. This is slope. This is saying this case, the first case, the slope is what? It's flatter compared to 1. So this is above. Let's see the second case. Again, this is diagonal. So 1, 1. Now, what happened to the slope? The slope at 1 is bigger than 1. That means you are steeper. But at f0, by assumption, we know f0 is what? F0 is, what's f? F0 is positive, right? So the only way you can have another, you see, you're going to have, there exists one interior fixed point, that's Q. The intersection between the curve and the diagonal will be a fixed point. Now we see this case, exactly we have 2 fixed points. One is the boundary point 1, the other one is the interior point, that's Q. What's guaranteed this? The slope. Because this slope is what? Is higher than 1, so it's steeper. But at f at 0 is not 0. We talk about that, that's the assumption, right? F at 0 is what? Is bigger than 0. So the only thing to worry about is this scenario, but now it's not going to happen. This one, right? This is f of t, but f0 is 0. You have no interior fixed point. However, you are assuming f0 is bigger than 0. So now you're not going to have that. That's it. Super easy and simple. Is the idea clear? we can use rigorous calculus to prove everything. But I think those two pictures mean solve those words. Does this make sense? And that's how we prove it. But the key take-home message we already talked about. First is, under what situation branching process might be a good model. And in general is when you talk about initiation of the situation. Like our case, this class simply focus on infectious disease. You can think about initiation of the infection. When you start with that, you can use this. Second thing, and there is a fundamental difference between deterministic and stochastic model. I think you guys have already noticed that. When R0 is bigger than 1, before we saw, it depends on the model, sometimes we end up some non-trivial endemic. That means extinction, sorry, there's no way you're going to extinct. However, the stochastic or the branching process model telling us there's still a chance, it's just how big. How big is determined by Q to the power I0. Oh, sorry. This only proves this case. And also what happened to I0? That's coming from independency. If you start with one guy, extinction probability is Q. Start with another guy, what's the extinction probability? Is they're independent. Is the probability the first guy, Q, times the second probability. So Q times Q is Q squared, coming from independence. Because the probability independence, remember, there are two events that are independent. The probability both events happen is same as the probability A times the probability B. So now you have this one, start with one infected, you produce this, start with another infected, you produce this. Now you have two infected. But now the extinction probability for this one is Q, for this one is Q. It's coming from independent, so it's straightforward. All right, I think we can have like 10 or 15 minutes break. And after we can come back, we'll switch gear to talk about totally different topic, something called target reproduction number. Okay, all right, so we'll be back 10:30. Let's take a break. Again, online folks, is everything going all right? You guys can see us, hear us fine, right? Kakendo, you can hear us online?
I mute the sound.
Yeah.
Yeah, we can open. Yeah, now you can.
So you can.
Yeah.
You can hear us fine, right? There's echo. Yeah. Okay, all right. So before we start, this is going to be the last section of the class. I want to thank everyone, even during the winter break, everyone. And for coming here, I don't know, all the way. You probably had to take a metro or some public transportation. And for some of you guys, and you will come to school and attend this class, it will still start at 9 a.m. All right, so I want to thank everyone. I do hope each of you guys get something might be useful for you later. And of course, and even though the class will end today, I'll be here 2 more months. So if you have questions, anything you'd like to discuss further, feel free to stop by my office and you know where to find me. And the other thing, also, I would like to say a special thanks to my fantastic host, Feng-Bin Wang. You know, like what Vicky said, it's like my agent. 中文叫什么？经纪人。然后特别感谢王斌教授。然后 I also would like to thank NCTS, the institute, for hosting this. And in particular, I would like to thank Vicky. And here we have very nice and student, here we call assistant, right? NCTS assistant. And all make these things possible, you know, like every time before the class, and usually one day before, they will check on the vision, find the optimal mark, right? Clean the board beautifully, And for me, I really appreciate the chance to use chalkboard. And in my university back now, and blackboard becomes something rare and rare. 我们的黑板都不见了，因为我们有 remote participant, so we need like something modern and digital. And anyway, let's start the second part, and we're going to talk about something called target. This is probably chapter 4. Target. Let's see, how many of us have heard this terminology or even use it before? Okay, so now if that's the case, let's do something everyone familiar. Can you tell us what's R naught?
Definition.
Whatever your understanding about this quantity, R naught, basic regression, right?
This is the average number of next generation produced by
Secondary factor, right?
But the terminology in secondary infection.
Yeah, average number of secondary infection produced by.
Yeah,
One
I have one comment about it.
primary phase. Yeah, otherwise susceptible population over the
Like
infectious,
one,
for the infectious period.
like my concern is, if we are discussing about ACIR model, and I have one index here, then it may produce 2 or 3 new cases, secondary cases. But it first goes to the expose, and there might be some loss in expose. And after some loss, and only go to the infectious.
Yeah,
So we are dealing about how many infectious generated by single infectious, or how many secondary cases generated by a single infectious.
Right.
Two different things.
right. What do we mean by the new or the secondary infection? Like say SIRK super clear, right?
Yeah.
What's he talk about? That's a good point. SEIR. Let's say SEI. Doesn't matter. You have exposed class. So what's the secondary new infection? Is talk about E, we talk about I, we talk about oral. In that case, they talk about E and I. E
I
and
think,
I.
it should.
Directly is E, I know, but they talk about is the average and E and I.
Because if there is new cases,
Yeah,
but that new case loss.
yeah,
will
that's
expose-
exactly, that's
You
the,
cannot produce the secondary cases in next generation.
yeah, so do you guys remember, we talked about malaria case, a vector-bound disease? So, and eventually when we saw R naught is a weird quantity. You guys remember that?
Yeah,
It's the square root of something.
yeah.
And one quantity is a product, square root, underneath the square root is a product, 2 quantities. One is capture the production from host to vector. The other one capture the production from vector to host. You have to go through 2 steps. So that's why we take a geometric mean. It's per generation. So this is the overall production in terms of whatever you produce. In that case, you talk about both the infected host, which probably humans, and also the infected vector, which is mosquito, both. So that's one of the reasons we're going to introduce target reproduction number. Very good point. That's a good motivation. Okay, all right. So we know why we care about R0. R0 is some quantity telling us something like that, right?
There's one problem about
Right,
this definition.
right. So why we care about R naught? Because typically saying, in many scenarios, what happens? If R0 is less than 1, what happens? The production actually gets goes down. Distinct, right? But when R0 is bigger than what happened? You expect what? The disease will persist. So that's the basic terminology or like the idea. But this is not to say true, it's not a universal rule. This is an important quantity. We know the bigger the R0, the more trouble we're going to expect. That's a general picture, right? R0. And then let's see example. So we saw SAR. It's a mass action. Density dependent population. We know how to write down this model. We have solved this 1,000 times, many times. And we know the R0 in this case is what? Beta, I'm going to call S star, divided, D is not a good word, but doesn't matter, downfall of D. Right? We know this. And what's S star in this case is lambda over D, some constant. Is the number, basically is the what? The size of susceptible population at disease-free. In other words, because the conservation of the population, that's the total population size. That's S star. Lambda over D. Now the question is, if I'm able to, that's all my susceptible population, to do, say, vaccination and to do any sort of control. And basically, the proportion control is rho. So now I reduce this. Let's use P. P is the probability. Through, say, any way you can do. This is with control. This is without control. Then when you start to think about this basic quantity and what happens, you're going to have a new quantity, which you replace S star by. Here's whatever left. You're not able to do anything. Say vaccination. If P is 1/3, you have 2/3 population, you're not able to do any type of prevention control, say vaccination. Now you have this. And we see this, and before we know fundamental, like we want to, if we want to eliminate the disease, our hope is what? To control this quantity, make sure it's less than 1. So if this is less than 1, this is telling us what? And we solve beta minus P S star plus gamma, which is what? Which is this, right? And less than 1. So if we solve that, and we see P is bigger than 1 minus R0. We saw this stuff. What's this? It's related to herd immunity. This is saying, suppose R0 is 2, you need to control at least 1/2 of the population to control the disease. If R0 is 3, you need to control 1 minus 1/3, which is 67% of the population, whatever the control way you're doing it, and to eliminate the disease. This is something we saw before, right? We saw this before, right? Then is it fraction control? Now let's see a second example. This is even simpler than the example we talked about in class, a simple model model. See. We have two population. One is what? One is so for students, you probably some reference on R0 if you're interested. For the history are not. Mr. Black. Mr. Black. This is the paper published in ACTA. Two 50 issue. So this paper is called A Brief History of R0 and the Recipe for Calculation. That's the first one. And second one is Huffman. You guys know Huffman? Huffman. Smith. And well, so the paper is called Perspective on the Basic Reproduction Ratio. Is published on Journal of Royal Society Interface, issue 2, 2005. And here's another. This is written by mathematician Jim Cushion, and now is retired from Arizona University. Anyway, and Jim Cushion and O'Dickman. The many gases of RNA are not. This is published on GTB, Journal Theoretical Biology, 2016. And more recently, polyabundant ratio. Production numbers of the infectious disease models, which published on infectious disease model. Infectious disease model. The chief editor of this journal is Chang-Hong, and probably many of you guys know him.他是 double fellow in Canada Society， 是加拿大的双重院士。Anyway， 两个 title 的院士。当然，最后一个你要想看R0赵老师的那个文章，我们书有一章就是讲R0的，不过那个就会比较 abstract。对，赵老师那本书里也有。Anyway， 这是第一个。我说对学生如果感兴趣R0的 history， 这里应该是不错的 reference， 可以去看一下。我们现在来看 malaria。我现在这个 prime 都是 DDT 的意思哈。 基本上就是我们课上讲的那个 Malaria model。然后parameter 名字可能变了，这个 SIR 是什么呢？是 host。这个是什么呢？这是 mosquito，是 vector。这个 human host follow 是什么 ？SIR epidemic。然后是 vectors 是 SI epidemic， 这是 mosquito 的。然后这个 lambda 1和 lambda 2就是我们之前讲的 force of the infection。然后这个地方就是 cross infection， 从 vector 到 host， 就是 host 被 vector bite 了以后它 infected。然后这个是说是从什么呢？是从infected host 它会影响 vector， 因为什么？即便这个 mosquito 它是 susceptible， 它如果 bite infectious 或者是 infectious human host， 它也会 become infected。Anyway， 这不是重点，重点是说我们如果 linearize 这个 system， 我希望现在同学如果你有机会试这个，你已经很熟了。linearize 这个 system， 在 disease free。disease free equilibrium 是什么呢 ？SIO。是 B 1除以 U 2是 B2除以 0。是为什么我趁这种推分写起来会比较简单 ？Anyway， 然后它的 disease component 是什么呢？是 I 和 V， 对吧？所以我们如果 linearize in terms of I 和 V， 我们得到什么呢？是 lambda 以 NV 减去 gamma 加 mu 以 I， 或是 lambda 2 N 这个应该是 N2 I 减去 U2 变成 B。然后我们用 next generation matrix method， 我们来算它的这个 K。K 是什么呢 ？K 我们定义它的每个 entry 是 Kij。我们现在就把它写出来。So how does it look like? Let's see. It's going to be 0. Gamma plus mu1。所以在这个 next generation matrix 里有两个 entry， 它是 0。那现在一样，如果我能控制什么？如果能控制，现在有两个 infected population， 或者有两个 population in the story。如果我能控制谁呢？我如果能控制人，我叫 type 1， 这是第一个 population type， 这是 vector 叫 type 2。假如说如果我能控制 mosquito， 这是可能的，我用那个 mosquito 有各种各样的它的 nest。pesticide 就是杀 mosquito 的这种方法。如果我说什么呢？我要能控制 mosquito， 那这个 N2 就会变成什么呢 ？P 是 probability proportion and control， 1减 P 就是 whatever left。那这个时候你看原来的 R0 是这样的，原来的 R0 是根号下。K11 K22 K12 和 K21， 原来的 R0 是这样，但是如果 under control 的我叫 R0P， 它是什么呢？它就变成了 K12 和 K21 1减 P， 为什么呢？原因是这个 K 就变成什么了呢？就变成了 K11还是0 K12不动，我没有。We didn't control anything for the host. N1 doesn't change. So what's the change? It's right here. What's the change? It's here. 换句话说，在这个 under controlled situation 谁变了？它变了 ，N2 变了，因为 total population 只有1减 P 的 proportion 是 without control 的，那它对应的 R0 就变成这样了，因为这个 quantity 就叫 K 什么 K21 rescale by K21乘1减 P， 是吧？就是这里的 K21 rescale by K21乘1减 P。那现在一样啊，如果你想 control 这个 disease malaria， 我们的 ultimate goal 我们是想让 R0 什么？是不是小于1？那这个是 equivalent to 什么呢？是 P 要大于1减去1除以这个 quantity。那这是什么？这事实上就是 right here， 这就是这个 quantity 是什么？这个就是 target reproduction number， 这个东西就是 target reproduction number。我现在想说的是什么？当我们进行 control 的时候，你的 strategy 是 separate。如果你 control host，control type 1，first type， 或者你可以 control vector， 现在是 mosquito， 那是 type 2。那我们做这个 quantity 的时候，SL 还没删 ，SL 的时候，这个是什么 ？control 的 proportion 是1减去1 over R naught basic reproduction。那如果我只控制其中的一个 type， 现在这个东西我定义为 T2， 这是我 control 的 proportion。我需要 control 1减去这个 quantity 这么多 proportion， 我才能 control the disease。Does this make sense？ 因为1减 P N2 是 proportion leave like before without any manipulation。有问题吗？就是一个 rescale 嘛，因为 whatever the proportion you can control。你看这个时候它就不再是 R0 了，是 something else。为啥不是 R0？ 你看这个 R0 的 square 看起来 logically like RT2， 对不对 ？R0 square mathematically looks like T2。那 what's this quantity？ 这只是 something like hyperproduction。Keep that question in mind. Hopefully, I'm not going to be arrested. 那个，如果是 simple story， 你看这就是 R naught。可是这个 case 下，这显然不是 R naught。如果数学上来看，这是 R0 square， 但是这个 quantity 现在我们定义它为 T2。这 T2 是什么？For finite dimensional case of matrices。那现在就是这样的，因为你不会 control， 因为是两个 separate strategy。这是说什么？这个问题是说 ，if I'm able to control mosquito, what's the proportion mosquito I need to do whatever the procedure to control, so I'm able to control the disease。那当然，同时另一个方向你也可以 control 人，对吧？那你会 ask 一样的问题，东西是一样的。那个时候只是把 N1 变成一个 proportion， 对吧？但是这个时候你没有 control everything， 因为你有 heterogeneous population， 你有什么？你有 infected host， 你也有 infected mosquito 或者 vectors。我是有问题吗？好，我们来看这个最开始这个 quantity 我叫 type reproduction number， 它是 Robert Hesby。他们俩在2003和2007发了2篇文章 ，talk about 这个 T。 我现在叫 type reproduction number， 我们叫 T。这个 T 是什么呢？我把 R0 删了，是 average number of secondary infection of a target type. One type of target type produced by one primary case of the same type. Of course, otherwise except the host virgin population over the infectious period. 然后它定了这个 quantity， 我现在想说的这个 R0 是不一样的，因为现在第一个 story SIL 的时候我只有一个 population， 对吧？第二个 story 我有至少2个是 heterogeneous population， 有 host 又有 vector。那我不同的 control， 这时候的 quantity 它不再是 R0。你看这个 capture 的是什么？是 everything related to 你的 target type。而且这个 produce 的这个 one primary case 很清楚是 same type， 然后他还得到什么样的结论？他得到这样的结论，就是说，第一个 1.1 over t 是什么？这个 quantity usually defines the proportion of the control. Proportion of the population, target population. Needs to be controlled. 那既然我们这个课是讲 infectious disease， 那我可以把它更 restrict to disease case to be controlled, to eliminate the disease. 这就是1 minus 1 over t. The proportion of the population you need to be controlled to eliminate. 还知道什么？这是 definition， 这是 quantity 它的 meaning。第三个是什么？第三个是记不记得我们刚才讲的 R0？ What's the relationship between R0 and T？ 他说 R0 对我们来最重要的是说什么？它是一个什么 stressful quantity。这说明什么 ？What does this mean? This means 作为 stressful quantity， 它俩是 equivalent。Amazing 哈 ，quantity 数学上你去算它是不一样的，数学上你去算它是不一样的。这个是说，如果 basic reproduction number is above unity， 那这 equivalent to say target of course 是什么？我们要知道什么？这个 T 要是 well defined， 不是 define all the time，OK？ well defined。当它是 well defined 的时候，它俩是 stay on the same side of unity。你高一，我也高一，你低一，我也低一，咱俩在 same side。那换句话说，为什么这 important 呢？你是 disease threshold quantity， 我也是啊。You are disease threshold parameter, so do I.
This T is R0P.
Huh?
R0P?
No. R0 is R0, T is T.
No.
No.
P. What is T here?
What's T? T2, I define whatever this quantity is. And mathematically, it's equivalent to say original R0 squared.
So this T is T2?
Yeah. Because we have what? Heterogeneous population. We're not able to do everything, right? If if I'm able to control mosquitoes, that quantity basically over there is telling us what's the fraction of mosquito I need to do something, right? You see the fundamental difference? The definition, why we write the R0 definition in the very beginning, that's the average secondary infection produced by one primary case over the infectious period. Or this one is everything is focused on target type. Whatever the type, right now it's a vector, right? That's a type. You see the difference, right? And interestingly, R0 and type reproduction number, they're both or equivalent threshold parameters. And last point is 1 minus the reverse of T is telling us the proportion of the things you need to control of the target type. Suppose in your disease case, you have what? You have infected target cell, HIV. You have virus. In that case, you have both the target cells and the virus. You have two populations. And if you are able to control either one of them, that's not the R0. That quantity is captured by something called type reproduction number. You guys with me? Okay. So now, I should provide reference for, I still want to save those. What should we do? Are you guys done with this one? This one?
So, yeah, for the control of the disease, like you should control this much fractions of mosquito.
Special type. Yeah, this case is.
Yeah, and my
mosquito.
question is, because you are in the time series data like that, like in 1 year, and at what time you?
No, that's another story. That's another story. That's another story. This is just simply telling you if I'm able to do this.
No. Yes. If you able to do this, because like if I get the P equals to 0.5, that means I need to kill the 50% mosquito.
Right.
Yeah, right. Then my question is, when I have to kill the 50%, it's from the beginning of the.
No, that's another story. That's the optimal control thing. This is saying whatever the time, if you're able to start to do this basically start from the as early as possible. But there's no specific timing to specify this. They say if you are able to do something, that's at least how much you need to do. It's just like a COVID case. And I don't know here, I think the vaccine is not free, right? Is the COVID vaccine is free in Taiwan? 就是台湾的新冠是叫新冠疫苗吗？是免费的吗？
Yes, in 2021.
I don't know. Is that free of charge? But anyhow, that's not the point. I'm saying is the government have to support everyone if that's free coming from insurance or whatever. But the government have to save certain amount of money and to decide. And suppose here is adult population. What's the fraction of adult? Now I consider age structure. So less than 5 and from 5 to 65 and then 65 above, 3 category. So then you ask, probably below 5 before we did nothing because we had doubt about the vaccine, right? Then you ask, suppose you are senior people, 65 and above. What's the proportion of vaccine I have to provide, right? That's related to many things. I have to get the vaccine and provide it to everyone. So this one can be answered by this. Does that make sense? The model, of course, has to be more detailed. You have to have structure, right? And different population type. The focus on the type, you are able to do something. Then you ask, suppose it's IDA population, 5 and not IDA, 5 is not above. So like 18 to 65. And what's the proportion vaccine you have to support for this population type? You can do that like this. Are you done with this? So now, let's type. However, sometimes I can do even less. Sometimes I can do even less. Say for waterborne disease. And
Yeah.
so which involve more than one transmission pathway. So for waterborne disease, typically they have transmission due to direct contact between host and host, person. And they also can become infected and due to the indirect contact, infected host with the environment. So you have at least two transmission pathways. But suppose you're only able to control one. This case, you cannot control one population type. It's a part of your transmission pathway. Say, what about disease? Suppose I'm able to provide or supply safe water, safe drinking water. That's only very specific, tiny part of your pathway. Then you ask, what's the effort I need to make? This case, type reproduction number is not sufficient. So then it's a concept, something called target reproduction. Back to you. Looks like you have questions.
I'm curious about how can I simulate a model like in this time? Because if I know that 50% mosquito, if I keep, then I can.
Implementation
Yeah.
and this quantity is a
Because-
different
because-
thing. It's a different thing. That's a very specific, meaning, given this one, I think this one is not telling you how to implement. It's giving you a guidance.
Yeah, and guidance means like.
No, I'm not telling you the detail. I only provide you like the government. Here's the guidance. I need to provide, suppose, safe water for if we have waterborne disease. Here we don't have, we have safe water everywhere, right? I think we have safe drinking water. Is that right? Even though the tap water is not drinkable. 我说那个水龙头的水可以喝吗？直接喝吗？不能，对吧？就 tap water is not drinkable. Anyway, we have clean water. But for the place, if you have this kind of issue, what I'm saying, and zoom in, I can only do certain part, very specific piece. In this case, basic reproduction number is not sufficient, type of reproduction number sufficient. I have to zoom in, look into very specific piece. So then, and people introduce this concept, yeah, target reproduction number. So let's call this T. T what? I ran out the T and the TS. So this is introduced by Zhisheng Shuai, Robert Hasbig. And Feng-Bin duration. This is GMB 2013. The search those three names with this, and they actually generalize or extend the concept type reproduction number to target. And later, 6 years later, Mark Lewis Mark Lewis is another Canada chair. Anyway, and he was the undergraduate student of Pauline Wendell-Risch. And Shuai was the postdoc of Pauline Wendell-Risch. My colleague, very senior colleague, actually also was the first postdoc, I think, Pauline Wendell-Risch. Anyway, so this is 2019. And what they did, this case, they extend type reproduction number to target. And in the later paper, they provide a general framework. For target reproduction number for non-negative matrix case. The first one is the extension of the concept. The second one is the unify of all the concept. And this approach unify what? R0, basic reproduction number, type reproduction number, and target reproduction number. So let's see what's this idea. We cannot write over there. Let's check. Do we have really anyone online? I want to save that because we need to come back repeat this. Online folks. Do refund. Oh, sorry, I saw refund. I have to. Sorry, guys. Are you guys done with this? So far, so good? All right. Sorry, guys, because we need to come back revisit this. 我们现在就来 let's take a close look. What's something really called target reproduction number? How I define it? How we're going to do it? What's this stuff? 我们现在看了这个 R0 是 overall 的一个 quantity。 Type 是 specific types, population type, 而 target 是 any specific piece. 它就 zoom in more and more. Let's see what's this quantity. Let's say K to be the next generation matrix. Okay, of course non-negative. And S是一个 subset. Index subset. 你可以想象 S 是什么？这个 next generation matrix 是一个 matrix， 它有 double index. I and J is S row, J is column, right? And now S is whatever the target index. Any subset, which is the target index. We can control what? One row, one column, any specific entry, that's S. Suppose we control the first row. Your case what? N by N matrix, right? The first row will K. S will be what? Will be 1, 1, 1, 2, 1, N, etc. If we control the first column, so the second index will freeze at 1, and now you vary the first index. Suppose we control any specific piece, then you just tell me what's S. Okay, all right. So that KS what? Be Kij if the index in your target set, in the target index set. Otherwise, 0. Then, and here is the assumption to guarantee this is well defined. assume the spectral radius, the remainder is less than 1. Then the target reproduction number P is defined to be, let's call TS, is defined to be the spectral radius KS defined to be the spectral radius. Oh, do we need to define this again? Spectral radius. R0 is spectral radius, okay. Basically, it's what? The maximal amplitude of the eigenvalue. So is for matrix case. So what this means, this quantity has spectral radius less than 1. Let's look at this. Matrix of M of A. Are we familiar with matrix extension? Under what situation this is invertible? First of all, the spectral radius of A cannot exceed 1, otherwise not revertible. Spectral radius of A has to be less than 1 to make sure this is revertible. And second thing, you just look at this. What's this? Any students remember what's this? What's the Taylor series expansion then? This one, right? So basically, the 1 minus x inverse is equal to this, right? So what we see from here, this is the one-dimensional function case. And to guarantee this one is invertible, we know the amplitude of this one has to be less than 1. So that's basically the one-dimensional analog of this. One-dimensional scenario of this. The spectral radius less than 1 is what? The maximal amplitude eigenvalue has to be less than 1, right? Okay, all right. Then if we expand this, this will be what? Right? You guys with me? So what this is saying, first of all, I have to make sure the whole thing is invertible. So that's why we're assuming the spectral radius is less than 1. Second thing, let's see what's this. And 1 minus is what? It's identity right? So now I multiply the whole thing by Ks. What do we got? We got Ks, K minus Ks. I'm trying to tell you what this means. What this quantity means. Look, this is what? This is your control part. K minus Ks is your the part you're not control, it's without control. This is a control part, this is non-control part. This is saying if this is a control part, first of all, I just do it directly. As this one is saying, I have to go through non-control part once before I'm able to control this. This is saying I have to go through the non-control part twice before I'm able to do this, and etc. When you put it together, you get this. Now you look at the spectral radius of this one. So that's the target reproduction number. Now, let's see. So it's accumulation. between what? Target, non-target part. That's eventually how you can do this. You can do this directly, but you have to go through the part you are not able to do anything once before you control it. You have to go through this procedure twice before you're able to control it. So it's accumulation of eventually the target control. Now you look at the maximum what? The spectral radius. So now let's see this. Suppose S is everything. What's that means? That means Ks is K. So K minus Ks is 0. So what we got? We got Ts in this scenario is RO, the spectral radius of K. Because this is 1 minus 0 inverse, right? What's that? What's that? That's R0, right? What's this saying? This is saying if you're able to control everything, look, that's everything. That's R0. Okay? So now let's this case. If I'm controlling everything, that's the fraction of the effort I have to do to moderate or to eliminate the infection. Now let's look at the malaria case. Malaria case, the only difference is you have what? 2 population type. 2 population type. This is saying I'm control everything. So target become R0. Second thing, let's look at this. Oh, maybe the better way. I think we don't need this anymore. Can I erase this? Let's see this. So now, if remember, the first population type is what? First population type is a whole, second population type is a vector. If I'm able to control the vector, what's S? You target a second population type. That would be what? 2, 1, 2, 2. Right? The second row. The second type. So then what's Ks? By definition, here is the Ks definition. I'm going to save everything like second row, K21, K22. And in our case, it's lambda 2, 2. Let me know if I copy anything wrong. I'm simply copy from the other side. This is Ks. What's the K minus Ks? Anything that's left. So which is 0, 1, 1 divided by mu2. Is this clear? Then by definition, Ts is what? The spectral radius of this. So if we calculate, we see this is a K12, K21. When I target at the second population type, when I control the second population type, that's exactly T2. So for simplicity, if you control first population called T1, second population called T2, and S population called Ti, that's just a simplification of notation. And now again, you see what's the proportional control I have to do for second population type? 1 minus 1 over t. So that's the, I think the guidance, the target reproduction number can provide you. And first take home message I want to emphasize. When you are able to control everything, what's that? That's when you are able to control everything, that's what? That's are not. When you only control certain population type, that means you only control certain rows. Like here, second population type, why I take 2, so you now see only the first row, I saw the second row. You can do the same thing for the first row. And do the calculation, you get the corresponding target reproduction number. And this case, indeed, also is type reproduction. But in general, if I'm able to control any specific piece in terms of next generation matrix, you just take it out, whatever the piece you are able to control. For anything you're not control, you put it right here. Then you calculate. This quantity will tell you and how you're going to control the specific piece, giving you the general idea of this. Is what quantity? The 1 minus 1 over t. Again, the larger the t, you see t equals to 2, 1/2. T equal to 4, that's 75%. So the larger the t, the bigger of the effort you have to make to control your component. You see that, right? All right. So now let's see. So generally, so we're done with malaria case. I'm going to clean everything here. Now, is the general picture clear? R0 is kind of saying, I'm doing anything overall. That's not possible, indeed. And type is saying, I'm able to control certain population type if you have a heterogeneous population, right? Any specific population type. A target is saying, if I'm able to what? To touch, to control, to implement, to manage any specific part of your infection story. So that you're going to need target. And how we unify, we saw that, how we unify all this quantity. It depends on S, target set. All right, so now, so target reproduction number. So let's for A is 2 by 2 matrix. Let's see what's this. Let's say the next generation matrix. It's just like this case. This is a 2 by 2 matrix. Let's do a simple exercise, okay? And let S to be our first step. This I and J could be any, now we have 4 different entries, any of those pieces. So then, by definition, we know TS equal to Tij is equal to what? I'm simply copying the definition, but the point is because 2 by 2, now you can do everything. Now here is Ij. Here is Tij. This is a 1, 1. Here's what you got. So next time when you have 2x2 matrix, you don't have to calculate, you have the formula. Because it's too. If everything has condition. What's this guarantee? This is guarantee the spectral radius of this one as the one is guaranteed. This inverse makes sense, meaning this matrix is invertible. That's this condition. Here is condition. This quantity is only defined if this is invertible matrix. So this is guaranteed this is invertible matrix. If this is 1, 2, here we got and 2, 1. Last one. And if you take a close look of all this calculation, you notice anything? You see anything different or special? You saw something special? Take a close look, the second one, T12 and T21. What did you notice? What did you notice? T12 or T21? Anything special? Yeah. Yeah, exactly. They're identical. They're twins. Is that interesting? Indeed, there is a general result for those. First comment. Suppose the next generation matrix K is irreducible. We already know what irreducible means. Means you cannot find a permutation such that this one can be rewritten up block of triangular matrix. Oh, if you look at the graph, that means the graph corresponding digraph is strongly connected. Anyway, irreducible, of course, type reproduction number has to be well defined. That's our general assumption. Then we have the following result. What's this? Symmetry. And second thing is, what's this? This is a transpose of the index. I'm talking about one entry. And second thing, S is the target set. But if you flip, who is the row, who is the column? Look at the transpose, they are identical. And second thing, or maybe the last thing, as an example, we probably have never talked about those in class before, have we? It's a waterborne disease. any order body. Doesn't have to be any specific one. So now let's see this. They have two populations in the story. One is the host, the human host. And the other one is a bacteria. Vibrio cholera, like pathogen. Okay, so now we're assuming first that so direct transmission and indirect transmission. Here is recovery and also R maybe become S again. So it's the SIRS epidemic for the host. And second thing, bacteria. So infected host can shed the bacteria into the environment. And bacteria cell can grow. The model is not that important. If we can write down this model, sorry, if we see the diagram, we all know how to write down this model. So I'm going to skip that part. So here is a waterborne disease. And now, even though we have two populations, host and the bacteria. So what's the infected or like disease component is I and B, right? I and B. So in this case, the corresponding looks like this. So here is just notation. But what I want to emphasize, even for this, what about this? And here, this piece, F, is coming from F1. What's F1? F1 is the direct transmission between hosts. F2 is the indirect transmission between host and the environment. All right. So now, let's do a bunch of different control. If we are able to do vaccine, of course, on host, what will be happen? So in this case, what will be your target set? You control what? You control the first population type, right? Do vaccination. The first population for the disease component, we have two populations. One is the host, the other one is the bacteria. You're able to control a host. So that's type 1. So this S will be what? The entire first row. Because this case, what's N? N, this one I didn't define. N is B or D or something like that. Okay, the first row. Then the corresponding TS is T1, type 1. We can calculate this. So this is of course provided this. And second thing, maybe we can do what? Control this one. This one is what? This one is the indirect transmission between environment and the host. How are you going to able to control the indirect transmission? For instance, because for waterborne disease, the source of the entire transmission of the key source is water, contaminated water. So if you are able to what? Clean the water, sanitize and clean the water. The water source, contaminated water. If you're able to clean that, what are you going to control? You're going to control only, you have direct transmission, indirect transmission, only part of those. So this case, the target set will be 1, 2. Very specific. In that case, then you just calculate T12, TS is T12, and we have the formula somewhere over there, right? Right there, T12. You just copy down and plug in what you got. Of course, provided then what else? If I'm able to, this is shedding. And in waterborne disease, what's the shedding? It's just like when we got flu, we will have a running nose, right? We will shed the bacteria into the environment. But for waterborne disease, how they're going to shed the bacteria into the environment? Either, just like remember when we had diarrhea, 腹泻的时候，它会 shed the bacteria through our feces， 粪便里排泄。那如果是粪便里排泄，就会称之谁 ？shedding rate。那这个时候 hygienic disposal of feces， 这是 2:1。Do we need to calculate this? Do we need to calculate this? No. 2:1 equal to by symmetry equal to what? 1:2. Same condition as the above, right? Or if we're able to quarantine the human host. If we're able to control quarantine the human host, we are able to control what? Direct host to host transmission. So S will be 1:1. Then you use a formula over there. So you will see this one equal to of course, provided this condition has to be hold, meaning the denominator has to be positive. To show you this very specific example, I want to tell you how useful and the target reproduction number can be. And this quantity is not our eventual target. We want to know if I'm able to control, say, one population type, 1 minus 1 over TS will tell you how much effort you need to do. If I'm able to clean what? The feces, 粪便。比如说到处都有排泄粪便的场所，如果我能做定期的常规的清理，那这个就告诉我这个 1 minus 1 over TS 可以告诉我什么 ？What's the proportion？ 这些场所，比如说现在我100个场地，然后 TS 等于什么 ？TS 等于 4， 那你说明什么？你要清至少 3/4 75%, 1 minus 1/4。你要清这么多的场地，这是提供这个 guidance。如果你做 quarantine，这个 content right here, 1 minus 1 RTS can tell you what's the proportion people you need to be if there are infected。当然不能 control everything，但是 that's your target， 对吧？好 ，I think we run out of time. We'll end here. But at least I hope I gave you some the key reference. The reference we talk about at the end is the Shrine, has the big, and the London Derisi 2013 GMB paper. That's the first extension from type to target. And second one is Mark Lewis, Zhisheng Shuai and Poland London Derisi 2019, same journal GMB. That's the unified definition of Harvard professional. I think that's all for today and for the entire class. I want to thank everyone again and for this journey. And so that's all. All right. Thank you.